Hello and welcome back to my channel. Today we're going to be talking about rates in context. This is going to kind of start us on our related rates journey. So we are going to start with some rates in context that aren't just straight line motion. So Speedville High School opens its doors to students at 8 a.m. each morning. On one particular morning, the number of students inside Speedville High School can be modeled by the function P of t equals, where t is between 0 and 8 minutes since the doors opened at 8 a.m. Find the rate that the number of students inside Speedville High School is changing at 8:03. So the first thing that we need to do is find our derivative. So p prime of t equals, we have 25 times the derivative of our natural log. So 3t plus 1 goes in the denominator. The derivative of 3t plus 1 is 3. This means we are looking at 75 over 3t plus 1. We're going to go ahead and plug in 3 because it's 8:03, 3 minutes after 8 o'clock. This gives us 75. 9 times 3 plus 1 is 10, so 7.5. This would be looking at our units, number of students per minute. So looking at this, the number of students in the high school is increasing at a rate of 7.5 students per minute at t equals 3 minutes. Oh, that is not how you spell minute. A lot of the time, the part that takes the longest is just writing that sentence to kind of wrap everything together. Okay, a rumor is spreading around school that Mr. Passwater once placed third in the World's Strongest Man contest. The rumor is spreading at a rate of dr over dt equals 1/4 r times the quantity 500 minus r, where r of t is the total number of students that have heard the rumor, and t is the number of hours since the rumor has begun. Is the rumor spreading faster when 200 people have heard it or when 400 people have heard it? So r of t is the number of people. R, which is our function's independent variable, is the thing that we're going to be plugging in. So we are plugging in the number of people. We don't really know necessarily the time, and we don't necessarily need to know. We just need to know the number of people based off our derivative. So we are going to be taking dr over dt. We are going to plug in r equaling 200 and r equaling 400. So 1/4 times 200 times 500 minus 200. 200 divided by 4 is 50. Times 300. 5 times 3 is 15. So we have 15,000. So when 200 people have heard the rumor, it is increasing at a rate of 15,000 people per hour. On the other hand, if 400 people know, we have 100 times 100. So we have 10,000 people per hour. So we can kind of make the decision that the rumor will spread faster when 200 people have heard it versus when 400 people have heard it, because the rate of change is higher at 15,000 than 10,000. And if we think about this logically, that would somewhat make sense, because if 400 people have already heard it, that's just less people that have the ability to learn it later. versus if 200 people have heard it, there are just more people to tell. Okay, so we're going to look at the rate of cars entering a toll road in cars per hour, modeled by CFT. During this time, cars exit the toll road at a constant rate of 200 cars per hour. Is the amount of cars in the toll road increasing or decreasing at t equals 9? So one of the things that we have to be careful here is CFT is a rate of change already. It is cars per hour. So we don't actually need to do anything super extra here because CFT is already what we kind of need it to be. So we're going to just plug in 9. So 9 minus 2 is 7. 7 squared is 49. 5 times 49 is 245. 400 minus 245 is 155. So we are going to be looking at this as 155 cars per hour, and this is specifically entering. 200 cars per hour is what is leaving. So to find out the amount of cars on the toll road, we are going to be subtracting those two. So 155 minus 200 to get negative 45 cars per hour. I don't really have room to write my sentence, but I would say the amount of cars on the toll road is decreasing at a rate of 45 cars per hour at t equals 9. So we just kind of have to keep in mind what our statement would be. This last one here, at a local library, visitors check out and return books throughout the day. The rate that the visitors check out books in books per minute, another rate, is modeled by our graph L of t, where t is measured in minutes. During the time, the total amount of books that have been returned to the library is modeled by R of t equaling 4t, where t is measured in minutes. So at what rate are the books being checked out to visitors at time t equals 9? So checked out is our L of t. So L of t, so we're just looking for L of 9 because it is already a rate of change. So our y value at 9 looks like it's 5. So this would be 5 books per minute. Is the amount of books at the library increasing or decreasing at 6? So we would look at the amount of books checked out versus the amount of books checked in. So the amount of books checked out at 6 would be about 3.5 books per minute. When we look at R of t, it is the total number of books that have been returned to the library over minutes. So this is not a rate. So we need to find R prime of t. R prime of t happens to be 4. So we know the rate that books are being checked in, no matter when, is going to be 4. So R prime of 6 is 4. If we are to combine them, the amount leaving and the amount returning, we have a positive return rate of 0.5 books per minute. So the books in the library are increasing at a rate of 0.5 books per minute at t equals 6 minutes. We get to our last one, at what time or times is the rate the books are checked out equal to the rates the books are being returned. So we know the rate the books are being returned, R prime of t, is equal to 4. So we need to figure out when L of t equals 4. So if we look at our graph here, 4 is right here. So this happens in 2 spots, right here and right here. So if I kind of look down here at 5 and 8, our rate of entering and rate of leaving are the same. So at t equals 5 and t equals 8, our rates for entering and leaving are the same. So this is just in context in general. In just a second, we're going to talk about the beginnings of related rates.